The last type of application problem we will look at in this section is a navigation problem, okay? So these are going to be problems that involve bearing, which we've already looked at. But you can also solve problems that involve bearing using vectors, okay? So this time you're going to see some problems that involve terms like airspeed and ground speed. So you should know something about that. So before we go into that type of problem, let's review these definitions. It says in air navigation, the airspeed of a plane is its speed relative to the air, and the ground speed is its speed relative to the ground. Because of wind, these two speeds are usually different. And then the ground speed of the plane is represented by the vector sum of the airspeed and wind speed vectors. I believe we're going to use this terminology in example 11. So when we get there, we will come back to this box. Okay. All right, so let's take a look at example 10. Okay, again, this will be a problem involving bearing, but we will just use vectors to do this. Okay, example 10, a ship leaves port on a bearing of 25 degrees and travels 61.4 kilometers. The ship then turns due east and travels 84.6 kilometers. How far is the ship from port? What is the bearing from port? Round distance to the nearest kilometer and bearing to the nearest tenth. Okay, so when you read this problem, it sounds just like the navigation problems we've done already. So really just work it like you're used to, okay? But just keep in mind, when we draw all these arrows, it's really a vector, okay? All right, so here we go. The ship has to leave port on a bearing of 25 degrees. Okay, so let's start with that. Okay, so I'm going to place a dot. Okay, this is going to be the starting point or the port. And so we know that the ship is going to travel at a bearing of 25 degrees. So I need to go ahead and put in my north, south, east, and west cross so I can do this bearing here. All right, so here we go. I'm trying to line this up. Okay, so here we go. Again, this is just a single angle that is being used to express bearing. So we know we're going to align ourselves with due north and then rotate in a clockwise direction if I can ever line this thing up. Okay, hold on. Let me just start over. Hang on. Okay, so here's due north, we hope this time. Come on thing. Sometimes using this thing is tricky. All right. Okay, there we go. That's good enough. Okay, so here we go. I'll put north, south, west, and east. Okay, so this ship is leaving the port. I'm going to align myself with due north, and I'm going to rotate clockwise by 25 degrees. Okay, so I'm just going to eyeball that. Maybe it's about here. Okay, so the only difference here, you don't have to do this, but in this vector section, you know, if you wanted to make it a vector problem, you would put the arrow here, like the ship sailed from here to here. Okay, but it's not a requirement to put that arrow on there. This is a 25-degree angle. Okay, we do know the magnitude here. Okay, the ship sailed a distance of 61.4 kilometers. Okay, so that is the magnitude of this vector. And then we know the ship turns due east and goes 84.6 kilometers. Okay, so we know the ship is currently right here. Okay, so now we don't even have to really put our north, south, west, and east crossed on here because we know the ship is just going to go straight east. Okay, so at this point, we will construct another vector to the east. We're going due east. Okay, and we're going to make this vector have a longer magnitude because it's traveling a longer distance. Okay, so the ship will now travel to here. Okay, this distance is going to be 84.6 kilometers. Okay, so the question is, there's two questions. First of all, how far is the ship from port? Okay, that is the first question. Okay, so basically we need to figure this out. Okay, so again, if you follow my cursor, the ship started at port, it sailed on a bearing of 25 degrees for 64.1 kilometers and ended up at this point, and then turned due east and traveled for 84.6 kilometers and then ended up here. Okay, so currently this is where the ship is. And so if we're trying to figure out how far the ship is from port, the closest measurement is going to be straight from the port to this point. Okay, so we're basically trying to figure out what this red distance is, or the magnitude of this red vector. Okay, so that is how we're going to have to work this particular problem. All right, let's look at our picture and see what we can do. Again, the goal is to find the magnitude of this red vector. Okay, so what I'm going to do here is I'm going to focus on this 25-degree angle that I have here, and I'm going to do some line extensions here. Okay, you know that is very helpful to do. Okay, so let me use the same color I had. So I'm going to extend the north-south line in this direction. Hang on. Okay, so I'm going to extend the north-south line in this direction. So like this, just making it a little longer. And then I'm going to extend this black line, but I'm going to use a different color so it doesn't interfere with the distance that the ship traveled. Okay, so I'm just extending these lines. Okay, this is a right angle because you basically have a north-south line intersecting with an east-west line. So if you look at this particular triangle right here, it is a right triangle. We know there's a 90-degree angle and we know there's a 25-degree angle. So if we do 180 minus 90 degrees, that leaves 90 degrees. And then if we take away 25 degrees, that is going to leave us with what? 90 minus 25 is going to leave us with a 65-degree angle. Okay, so that means the measure of this angle is 65 degrees. Okay, but if you focus in on this line, if you see where my cursor is, this east-west line that contains the 84.6 kilometers, that is a straight angle. So basically this angle in the triangle, this blue angle, that's 65 degrees, if I add this angle, that's going to be 180 degrees. Okay, so now I need to do 180 degrees minus 65 degrees, and that's going to give me an angle inside of this oblique triangle. Okay, so let's see here. If we go 180 minus 65, that's going to give us 115 degrees. Okay, that is the measure of this angle. Okay, so now this right triangle helped us get information about the oblique triangle. Okay, so let me kind of redraw what I just erased here. Okay, so we know I did this. Okay, so now that we know this angle, we are going to turn our attention to this oblique triangle. Okay, so when I look at this, okay, I know three things, and you have to go in order. I know the side, I know the angle, and I know the side. Okay, so this is a SAS problem. Okay, we know for SAS and sides, we use the law of cosines. Okay, so I need to go ahead and put some letters on here. So I'll call this vertex A, this is vertex B, this is vertex C. Okay, so I know the side across from angle B is going to be side length B. Across from angle A, that means that A measures 84.6. And then if I draw across from angle C, okay, that means that the length C is 61.4 kilometers. Okay, so we are trying to solve for this red vector. Okay, it's no longer red because I shaded the blue here, but we're looking for this red distance right here. Okay, that is our goal. Okay, so we need to find the measure of side B here. Okay, so if you go back and look at the variations of the law of cosines, we are going to use the version that's going to allow us to solve for B squared. Okay, so this is going to be A squared plus C squared minus 2 times A times C times the cosine of angle B. Okay, so we should be able to plug in for lowercase a, lowercase c, and angle B. So B squared is going to be, side A is 84 0.6 squared plus c squared is going to be 61.4 squared minus 2 times a times c times the cosine of angle B, which is 115 degrees. Okay, and this is going to give us a measurement for B squared. Okay, so let's go type it in. This is going to be 84.6 squared. Oops, hold on. 84.6 squared plus 61.4 squared minus 2 times 84.6 times 61.4 times the cosine, make sure you're in degrees, of 115 degrees. Okay, so here is our measurement for B squared. So 15,317.65041. And then I need to take the square root of this, okay, to get B, okay. We are dealing with a distance here, so you can ignore the negative square root. Okay, so this is going to be 123.7644957. Okay, so that's the distance we're looking for. Okay, it says in the directions to round distance to the nearest kilometer, and so we have a 7 after the decimal point, so we will bump up to 124. Okay, so the distance from the ship to port is approximately 124 kilometers. Okay, you have to put units when you're doing these application problems. Okay, all right, there is a second question. Okay, so we have to go back and answer that. Okay, the other thing we need to answer is, what is the bearing from port? Okay, so what is the bearing from port? Well, let's mark this bearing on the picture. Okay, so I'm going to use a bright color here so you can see it. When I draw the bearing, remember it is an angle measured from due north. Okay, so I'm going to line myself with due north, and I'm just basically going to rotate until I get to this red vector. Okay, so this is going to be the bearing right here. Okay, this angle, bearing. Okay, so notice this bearing, this orange arc, it is made up of this 25-degree angle right here, and then this angle right here. Okay, so let me mark this with something else. So this ice blue that I'm drawing in here, okay, I need to figure out the measure of this ice blue angle and then add it to 25 degrees, and then that will give me the bearing. Okay, this blue angle is basically angle A of my oblique triangle. So I need to solve this oblique triangle now for angle A. Okay, it's not as easy as subtracting from 180 because we only know one angle inside of this triangle. Okay, so if you look at it, we just solved for side length B, and I know the full decimal expansion. Side length B is going to be 123.7644957. Okay, I know all three sides of the oblique triangle, so this is going to become a side case. Again, we're going to apply the law of cosines to get angle A. Okay, so if we are solving for angle A, we need to use the version of the law of cosines that has angle A in it. Okay, so that's going to be this version. A squared is equal to B squared plus C squared minus 2 times B times C times the cosine of angle A. Okay, we are solving for angle A. So before plugging everything in, I'm going to solve this for the cosine of A. Okay, so I'm going to move the B squared and the C squared over. So I'm going to get A squared minus B squared minus C squared is equal to negative 2 times B times C times the cosine of A. Okay, divide both sides by negative 2 times B times C. Okay, and that's going to tell me how to get the cosine of A. I'm just going to switch sides here. Okay, so on this side, these guys will cancel. Okay, so the cosine of A, to get that quantity, we're going to do A squared minus B squared minus C squared all over -2 times B times C. Okay, now I'm going to plug into it. Okay, so the cosine of A is going to be A squared. Okay, so side length A is the 84.6 kilometers minus B squared. B squared, B is the decimal. Make sure you use the entire decimal expansion for accuracy. Okay, minus C squared. C is, if you go back to the picture, C is the side across from angle C, so that's the 61.4 kilometers. All of that is over -2 times B times C. Okay, so we're going to pop this in the calculator to get the cosine of A. Okay, if I go to my calculator, I'm going to go ahead and store this in B, letter B, for side length B. Okay, that way I don't have to keep retyping this. Okay, so let's go ahead and put the numerator in here. This is going to be 84.6 squared minus, I'm going to call it B. We're going to square that. And then we're going to subtract C squared, which is 61.4 squared. And this is going to give me the numerator. And then I'm going to divide by the entire denominator. I need to be careful and put the whole thing in parentheses. So this is going to be -2 times B times C, which is 61.4. Okay, so this is what the cosine of angle A equals. So 0.7849866. Okay, we're trying to solve for angle A, so we need to take the cosine inverse of both sides. Okay, so I'm just going to rewrite all of this, and then we'll pop it into the calculator. All right, on the left, the cosine inverse and cosine will cancel, leaving us with angle A. All right, so here we go. So we're just going to do the cosine inverse of this result. And there we go. Okay, so let me write this out. And we're in degree mode, so this is a degree measure. All right, so it's this many degrees. Okay, we do need to round to the nearest tenth according to the directions. It says at the end to round bearing to the nearest tenth. So we're going to say that this angle A is approximately 38.3 degrees. Okay, this is not the answer. Remember, the bearing is this orange angle. Okay, so we have to take this angle A inside the oblique triangle and add 25 degrees to it to get the bearing. Okay, so I'm going to come over here. So I'll put it back in orange for bearing here. Whoops. All right, so the bearing is going to be 25 degrees plus angle A. Okay, so this is going to be 25 degrees plus 38.3. And this is going to give us a bearing of 63.3 degrees. Okay, here is the answer. All right, so if you go back to your picture and think about what this means, okay, so this orange angle, okay, if we align ourselves here, I'll put a line segment on this. If we align ourselves with due north, okay, we have to rotate clockwise by 64.3 degrees to get along this red vector. Okay, so that's what the bearing means in this problem. Okay, so we are done. We have found both the distance of the ship to port, and we have found the bearing.